computer. Okay, great, great. Okay, so I have participants here. Let me actually put the text box up to make sure that I see the chat on my primary screen. Where'd it go? Chat, where'd chat go? Let me stop sharing and see if I can't find chat. Where'd it go? Oh, there it is. It's way over there on the wrong screen. That's what I get. All right. Okay, so chat now is open. Let me go back to sharing screen. All right, we should all see that now. And let me go ahead, and I have already started recording, so that's great. All right. So as far as administration goes, welcome to this week. We're in week 4. So we only have this week, and we're going to cover 4 chapters. And then we will be, here, let me stop sharing for a minute. We're going to cover 4 chapters in this week. And this week has a common theme. We're going to deal with the C double bond O, okay, the carbonyl. And it's going to be on all 4 chapters. And the cool thing is, its reactivity, you'll see it, well, it looks different from chapter to chapter. It's actually the same. So we have a nice common theme to drive this whole week, okay? So that being said, last week I inadvertently left the due date for chapter 11 through the weekend. And so some of you didn't finish it during the usual time of Friday at noon. So I have opened that up till noon tomorrow. So if you did not finish it, go ahead and finish it, and I'll correct the grades there. All of the chapters for 12 through 15 are due on Friday before the exam. So please, I'll be releasing all of those this afternoon. And so you'll have all of those due by Friday. And also the 10 additional questions. I'm going back and adding questions and editing questions to the previous chapters to make sure there are at least 10 representative questions for every single chapter that we can use to help us review for the final, okay? So again, that will help us with those. And so as we get closer to the final, which is next week, what I want you to do is like go ahead and review the 3 goals for each of the chapters, and then look over any videos for details you may have missed. And then go ahead and look at the questions. The style of the questions in the review, in the self-test, should be the same as the style in the exam, although it should be a little harder on the self-test than in the exam. I'm trying to make them simpler, asking only 1 question at a time. So you should see that similarity in there, and just maybe, you know, make sure you're answering the question I'm asking, which is usually a simple 1-step problem, occasionally 2 steps, but I'm trying to be very clear on what I'm asking on those. Our 3rd group project will be this week on Thursday. And I believe it's on carboxylic acid multifunctionality. We're going to go through a whole series of different carboxylic acid reactions, and so that'll be kind of the top hat will be, I'm sorry, the final will be presented on top hat during our regularly scheduled final, which is, I believe, on Wednesday, January 2nd. No, it's a Thursday, July 2nd, from 2 to 4:30 p.m. So it will be live on there. I will be monitoring that as well, as usual. And so we will have that. So we have 3 days next week. 1 day is going to be chapter 16. And then we'll have 2 days of review, including a makeup for activity number 1, which we didn't get to. So that will all be following this week. Okay, moving on with administration, our 4th exam will be on Friday of this week from noon to 1:40 p.m. Chapters 12 through 15. Again, the commonality here is that carbonyl function C double bond O. And then there is no faculty meeting scheduled for Friday, so happy hour, half hour at 2 p.m. Kind of also, it helps me gauge what kind of things to include in the review. So go ahead and chime in things that you would like a little more detail on during that, and we can make sure that that is on the review that we'll be having on Tuesday and Wednesday of next week. Okay, so those are the top 5 things for this week. What I'd like to do now is shift over to the goals for chapter 12. Okay. If you have any questions, go ahead and use the chat room here. I also have participants list here so I can see how many of us are coming in. Okay, and let's share our screen. Uh-oh. My iPad, there it goes. Okay, so there we go. So you should have all the videos for the rest of the semester posted. And so if you did, need to work or something over the weekend, you can go ahead. All the homework will be posted today so that you can also get ahead, including the homework for chapter 16, which won't be due until next Thursday. So if you need to catch up or get ahead, that would be an opportunity for you to do so. Okay, so aldehydes and ketones. So this is the first chapter where we introduce the carbonyl group, but the next 4 chapters all involve reactivity and what that carbonyl group does for us as far as functionality and reactivity. So our 3 goals for chapter 12 here are, the first thing is nomenclature, and that's specifically the aldehydes and ketones. And then goal 2 is what we call enol-keto tautomerism. And so in this tautomerization, we have basically 2 or 3 different resonance structures that, well, we may not have it very often in one structure versus the other. One structure is going to be a lot more reactive. So we know it's happening, even though it's happening in a very small amount. And then the last thing we're going to do is the reactions of ketones and aldehydes, including addition reactions and reduction reactions. But most of them are going to be what we call addition reactions. We're going to take that double bond back down to single bonds. Okay, so let me go and see if I can't get this to share. There we go. All right. So in all of these, the common theme is what we call the carbonyl group, or the C double bond O. Okay, and so the reactivity has everything to do with this bond, and it has to do with the idea that the carbon is going to be partially positive, the oxygen is going to be partially negative, and there are possible resonance structures associated with that. So if we think about that carbon always being partially positive, you're going to start to think, oh, well, that means nucleophiles are going to be attacking the carbonyl carbon. Okay, and that is the correct way to think about this. Okay, so we're going to do aldehydes and ketones, then we're going to go up to carboxylic acids, which have an additional electron donating group on them, and then there's derivatives associated with that, which are also basically just ways of taking an OH, which makes it a carboxylic acid and turns it into other electronegative things. And then the enolate ion is a slightly different one because of its electron join group, we're going to change the acidity of hydrogens near the carbonyl, but not on the carbonyl. So that's where we're going to be going with this. Okay. So the idea here is that if we just have the carbonyl group and there is a hydrogen bonded to this carbonyl group, it becomes what a functional group we know as an aldehyde. The simplest of this is what we call formaldehyde or methanaldehyde. Methanol. I need a pen with a stylus on it. All right, let's start with red ink here. All right. Formaldehyde is the simplest aldehyde we have, and we have basically a hydrogen bonded to the carbonyl on both sides. Okay, and what this gives us is a different kind of reactivity. Okay, now if we have a carbon-carbon bond on both sides of the carbonyl, we have a different functional group. And so that different functional group is now the ketone. Okay, so notice that's the big difference, is that there's 2 carbon-carbon bonds on that carbonyl, Here, there's only one, there's at least one carbon hydrogen bond to make it an aldehyde. Okay, if we have two, we have the simplest aldehyde. If we just have one, we have all the other aldehydes. But if we have no hydrogen bond to that carbonyl, we now have a ketone. Okay, so that's the simplest definition of each of them. And methanol, or formaldehyde, is the simplest aldehyde, and propanone, or the common name acetone, is the simplest ketone. It's the smallest organic compound that we can have as a ketone, because we have a carbon bond to each side of that carbonyl. Okay, so let's talk about why this happens and what makes it so reactive and has its what its hybridization is. So the first thing we think about is that the carbon itself is sp2 hybridized, meaning it has a p orbital with an oxygen in that p orbital. I'm sorry, an electron in that p orbital. And the oxygen is also sp2 hybridized and has one electron in that orbital. Okay, so what that means for us is we have our nice sigma bond here in the middle, and then we have a trigonal planar structure for it to bond those two other times. So the carbon side is going to end up bonding to two other things besides that oxygen. Okay, so what that also gives us is, because we have this p orbital that's hybridized, we're going to overlap those here, creating a pi bond. So we have our sigma bond in the middle with two electrons in it. We have our pi bond overlapping that with two more electrons in it, but that oxygen had 6 valence electrons. So we can't forget those. So what we have is we have 2 lone pairs sticking out here. Notice they are also trigonal planar, and they're also in the same plane as the 2 groups that are hooked up to the carbon here, okay? So that makes this nice flat molecule, okay? So that tells us some things about how things are gonna react. First of all, if something's gonna come and add across the double bond, it's gonna come in from the top or the bottom and add across those p orbitals. If, when we look at the electronic structure, we see that this oxygen is actually the partially negative side, because look at all those electrons, all those lone pairs. And this carbon side is going to be partially positive, okay? Which means anytime we're going to have a nucleophile come in and attack it, it's going to attack the carbon side. Anytime we have an electrophile come in and attack it, it's going to attack the oxygen side. And so just looking at the materials we're starting with, we should see which side of the carbonyl any species will attack. And so we can just use it from a simple acid-base theory or a partially positive, partially negative theory to figure out where things are going to react. Okay, so let's name these things. And let's see. There we go. Okay. There we go. Okay, so aldehydes and ketones rank higher than alkenes and alkynes, which means they change the end of the word, okay? So if we have just an alkane, we had an E at the end, or an alkene or an alkyne, we had an E at the end. We're gonna drop that E and add AL for an aldehyde. And it's easy to remember because we have al is the first part of aldehyde. Well, al is also ending all of our alkanes with aldehydes in them. And when we have a ketone, we end with the -one. So that's kind of a good way to remember it, is -one is at the end of all of our ketones, okay? Now, if you do have an unsaturation in there, like an ene or an ine, you still include that in there, because remember, the AL and the ONE go at the end where the last E was, okay? So you do include both of them, okay? So we'll do a couple namings on these to make sure we get this pattern down. Now, if you have a cyclic molecule, because you can't just add an al to the end of it, what we end up doing is actually adding an entire word called carbaldehyde. Okay, so we're naming it as an aldehyde, showing you that it has that carbonyl on it, and the carbonyl carbon is outside the ring. Okay, so that's why you have to add the entire word carbaldehyde to the end of the word. So let's do a couple examples of that right here. So to make sure we have an understanding of what's happening here, so with our rules, our uh, nomenclature rules, we of course start with the longest chain, and then we start numbering from what we named the parent for. In the first one here, we have an aldehyde, therefore we're going to name it for the aldehyde. So we're going to have Al at the end, an Al at the end. And so let's figure out how many carbons we have, including the carbon of the carbonyl. Notice our 1 starts at the carbonyl, 2, 3, and 4. So we have 4, so that's butyl. So there's no alkenes in there, so it's butane. So it'd be butanal, B-U, butane, B-U-T-A-N-A-L, butanal. So that's just the compound itself, but we have a substituent. And because we're naming from the carbonyl, because that's naming the parent, that puts our first substituent here at the 3. So we have 3-methyl butanal, okay? Now notice in the next one over, we have an alkene, okay? So we have to name it for the longest parent chain, including the alkene in it. And in that case, we have a total of 3. So that makes it propene. Propene. But instead of the E at the end, because we have an aldehyde, we're going to say propenal. Okay. So the al is naming it because the aldehyde's a higher priority than the alkene. And we still have to kind of name where that alkene begins. Because that alkene does not begin at our number 1 carbon, we have to call it 2-propenal or pro P 2 enal. Okay, so 2-propenal is probably the easiest way to write it, but you could write it either way if you wanted to be very clear where the alkene was. Okay, so that being said, let's name this last one here with our rules right here. So we have 2 alkenes, so we have to name for that. We have a chain, and we have the aldehyde at the end of our chain, so that's where we have to start our numbering. And so if we just started with the numbering system right here, we have 8 carbons, so we would have octa, but we have 2 alkenes, so we have octadiene, okay? But we have an aldehyde on it, so we have to end with Al. So it's going to be octadienol. So let's see, O, octa, octa, and then we have one alkene start on this 2 and the other one start on the 6. So 2, 6 diene right here, but we end with an aldehyde as our name, so it dienal right here. And so we also have a 1 and a 2 methyl groups, and they are specifically on the 3 and 7 carbons. So we have to go 3, 7, dimethyl, okay, octadienol, okay. Now, are we done? It looks like we have alkenes with more than 1 substituent, so we actually have to look at them and say, are they, do we have cis or trans, or do we have E and Z? Okay, so in the case of this 2,3 carbon, that turns out it's going to have the 2 highest priority groups opposite each other. Go ahead and double check me. And if they're opposite each other, that means that that bond, the 2,3, is an E, right? So it's 2E. And then this last one right here, we have a quandary because we have on one side, the 5 is definitely a higher rank than the 6, but on the other side, we have 2 methyl groups, therefore we have no priority. Therefore, we don't have a cis or trans isomerization on that one. So, but if we were to assign the stereoisomer for this alkene, it would be an E. Okay, so everybody's still with me on that so far? Okay, so when we name cyclic, it's easier, you name the ring that it is, and then you add carbaldehyde on it. So this would be cyclopentane, carbaldehyde. Oh, okay, that says aldehyde, trust me. Okay, so, and then of course, if we have substituents, because the carbaldehyde is naming the ring, we always start with that as number 1. So when we name the second one over here, we're going to name it cyclohexane. So it's going to be 4-hydroxy cyclohexyl carbonyl. Okay, and we actually can assign a stereo center. No, we can't, because there's symmetry on there. So there's no stereo center on the 1 carbon or the 4 carbon. Because if we go around this way, these are going to all be the same. And if we go around this way, they're all the same. So we don't have to worry about an R or S on these because they really, because of symmetry, have the exact same group. Okay. So now let's name some ketones for us, since the aldehydes we've done there. We're going to do the same thing for ketones. When we have a ketone in a ring where the carbonyl is in the ring, it's actually included in the name. So in something like this right here, the ketone starts the ring and labels it number 1. So we have cyclohexanone. So we drop the E and add O-N-E, so cyclohexanone for that. But we have a substituent, and this has to be number 1 because we're naming it for the ketone. And therefore, that makes it this, the 2-methyl cyclohexanone. All right, let's name this one right here now. We have 1, 2, 3 carbons total. So the common name would be dihydroxyacetone. Notice a ketone is higher in priority than an alcohol, so it takes the parent name. So if we were to name this in IUPAC terms, we would name that propanone. So it'd be 1, 3 dihydroxy propanone. Propane. No, because there's 3 carbons in the chain, and the simplest ketone actually is propanone. So we could add a 2 here, but it happens to be understood because that's the only place the ketone can be. But to be more precise, we'll add the 2. So 1, 3 dihydroxy 2 propanone would be the correct IUPAC name for this first one. All right, and then let me do this last one here. Let me see if I can just blow it up, maybe draw it with a smaller pen here. Okay, so this one is 1, 2, 3, 4, 5, 6 is the parent carbon, so that gives us hexanone. But because it's not necessarily symmetrical, we have to show where it is, so we have to name it 1, 2, 3, 4, 5, 6. Okay. Now, you might be thinking, okay, wait, hold up, we have a substituent. We should name it for the lowest substituent first. If they were equal, yes. However, because we're naming it for the ketone will always take the lowest position. When the ketone takes the lowest position, if we labeled it from the other side, we'd end up with 4-hexanone if the methyl group was on the 2 carbon. So that makes it not the correct numbering system. So we have to number from the other side and give the ketone the lowest number of 3, which puts our methyl group here on our 5 carbon. So we have to follow our rules. Remember, longest chain is where you have what's naming the chain at the lowest position, like an alcohol or the aldehyde, or in this case, the ketone. So that's why the methyl group here is here on a slightly higher number, because our ketone had to take priority. Okay. So then we actually have some common names for some of the ketones here. So when we have a compound, and we'll learn that this part right here is the part of acetic acid. And so that's why we call this aceto for the acetic acid portion, phenone for the phenyl group, and one because it's a ketone between the acetyl group and the phenyl group. So acetophenone is the common name for this. It actually has a really pleasant smell, and so we can use that. And therefore, if you had a ketone that was in between two phenyl rings, we call it benzophenone for having the benzyl groups and the ketone right here. Okay, but again, those are common names. Okay, and it would be very difficult to name this with the IUPAC name, so we use the common name. Okay, so that's the general idea here on naming those, but let me do one more thing and draw your attention to priority. Okay, by priority, we mean which functional group takes precedent over the other functional groups. When we started out, we just had alkenes, alkanes, and alkynes, and then we started adding groups to it. Okay, as we named halides, we said that they are always a substituent. They never change the parent name. And if we had sulfur and amino groups and they were the only groups on there, it could change the name into a thiol or an amine. However, if there was any higher group, they were a substituent. So in this case here, amino is one of the sulfuryl amino, and the halos are the lowest ones and are typically, if there's anything higher than them, they are a substituent. The next higher thing is alcohol. So if you have an alcohol and anything like an amino or a sulfur or a halide, then you name it for the alcohol. Okay. Now, if you have an alcohol and a ketone, you have to name it for the ketone. Okay. So ketone takes precedent over it. However, if you have an aldehyde, you name it for the aldehyde, even if you have a ketone present. So how do we name something that has a ketone and a carboxylic acid? Okay, so what we do there is, instead of naming the tail end like ONE for a ketone or AL for the aldehyde, we actually use it as a substituent now, and that substituent name is called oxo. Okay, so let's use this as an example here. Right here, you have a total of 4 carbons here, which gives us butane. Okay, we have an aldehyde and a ketone. And I just told you aldehydes rank higher. Therefore, aldehyde is what we're going to name the compound for. So that gives us butanal. Okay, butanal. And then but we also have another functional group there. So we have to indicate where that ketone is. And that ketone happens to be on this 3 carbon here. Because it's on this 3 carbon here, we call it 3-oxo butanal. Okay. Now, the tricky part is that if we have an aldehyde on a carboxylic acid, we end up using the same prefix, okay, which is the oxo prefix. So in the case of this compound right here, we have a total of 1, 2, 3 carbons with a carboxylic acid. So we have propane, and we're going to call that propionic acid. We'll learn that. We'll learn some more nomenclature in the next chapter. But the fact is that the aldehyde is less priority than a carboxylic acid. Therefore, we have to show which carbon it's on and name it oxo. Notice oxo can mean an aldehyde or a ketone. So, but it's any carbonyl that is of lower priority than the main group. So you'll see this a lot on carboxylic acids in particular. Okay, so now what we're going to see is in the next chapter, in chapter 14, we're going to see all the different derivatives, and we'll be able to make a really good nomenclature chart of all the highest priorities and all the different derivatives. So that'll be the last of our nomenclature adds. So this priority of these functional groups here is really something good to like maybe organize in a table to show that how you would name these for parents. So this is something maybe you should make a note of, that you should add a few of these into your nomenclature studies. Okay, so like I said before, IUPAC names are really great and very specific. However, because some of them are used so much, they actually have some common names. And one of the most common names right here is the simplest one here, this formaldehyde. It only has a carbon, one carbon. So if we were going to name it IUPAC, that would be methyl. So it'd be methanal. However, it's commonly used in formaldehyde. And some of you may know it. It's quite a strong carcinogen. So we try to minimize as much as we can out of our manufacturing processes. But then if you just take off one of these hydrogens and add an OH to it, right here, we've now turned it into a carboxylic acid, okay? But it still has a formaldehyde on it, so we call it formic acid, right here. The next simpler one is with a methyl group here, and if we took this off and added an OH here, we'd have acetic acid. So that's where the this beginning acida comes from. So the acetaldehyde is our common name. And then of course, by oxidizing this down to an acid, we have our nice common acid, acetic acid. Okay. So there are some names for ketones. The simplest common name for a ketone is acetone. It's a really good solvent. It's just got a methyl group on either side here. And then the next common one used in manufacturing is what we call MEK, or MEK, methyl ethyl ketone. So when you have common names, you typically name them for their alkyl groups. So for example, if it's symmetrical, we can say diethyl ketone, but if it's not symmetrical, it's methyl ethyl ketone. And again, it was named by engineers, so they didn't alphabetize it, but it makes a nice little acronym, MEK. And then if you have symmetrical ketones, it would just be whatever the two alkyl groups as a di. In this case, dicyclohexyl ketone. Okay, so let's talk about why it has the reactivity it has. Now that we know how to name them, aldehydes and ketones both have this carbonyl functionality. And this carbonyl functionality has a distinct polarity. Okay, so because of the lone pairs over here on the oxygen here, the carbon is always partially positive, and the oxygen is more electronegative too. So it's pulling, the sigma bond is also pulling it in that direction a little bit too. Okay, so if we were to actually draw a resonance structure of this carbonyl group, we could draw a resonance hybrid where we actually had a positive charge on carbon some of the time and the negative charge on oxygen some of the time. So that being said, if these are resonance structures of each other and it's flipping back and forth, that means that we're going to have definitely this partially positive side of the carbonyl right here on this side where the carbon is, and this partially negative side of the carbonyl where the oxygen is. Okay, so this leads to a couple different things. The first thing it leads to is the idea that we have a polar compound. Okay, because we have a net dipole going in this direction here, we actually have a polar compound, and so that affects its boiling point. It has a dipole bond that it can make with other materials. Therefore, it raises the boiling point for alkanes because of that dipole-dipole interaction. However, it's not as strong as hydrogen bonding. So it doesn't change it as much as the things like alcohols and amines that hydrogen bond. Okay. So does everybody see that this key feature here of the carbonyl is that carbon is partially positive. There's a dipole moment where the positive side is on the carbon and the negative side is on the oxygen. That creates a polar compound, and that creates our reactivity for everything we're going to do for this substituent. Okay, so if we look at equal molecular weights for an ether here, which is something with an oxygen, but it doesn't hydrogen bond, and it's polar, then we have the pentane, which only has our van der Waals forces, and the butanal, which has the carbonyl. We see the boiling point for the van der Waals forces are fairly low in the 30s right here. Just by adding that carbonyl and getting that dipole-dipole interaction, we're almost doubling the boiling point, okay? Now the ketone has the same effect here. Notice this ketone's about the same molecular weight, has about the same bonding here. However, if you add one thing that can hydrogen bond the alcohol, it jumps again. And if you add the carboxylic acid, which actually forms a different kind of hydrogen bonding, it even raises it even more. And we'll see this again in the next two chapters, that the carboxylic acids bond slightly differently for hydrogen bonding. But as we go up, we have van der Waals forces, then we get dipole-dipole interactions, then we have hydrogen bonding, and then we have carboxylic acids. So that's what we're going to see is the greatest effect on these boiling points and melting points, is the interaction between the different molecules. Okay? And that leads us also to some solubility issues. If you have a carbonyl, you have a dipole moment. In that dipole moment, you can hydrogen bond with water. If you can hydrogen bond with water, it actually will react with it slightly to form what we call the hydrate, where it literally you're adding water across that carbonyl bond. Now, that is a reversible reaction, so you can get the carbonyl out if you get rid of the water. But the idea here is because you can hydrogen bond, because you can form these hydrate complexes, you can get very high solubilities in water for lower molecular weights. And then as you get 3 carbons, it gets a little bit lower, and 4 carbons, that aldehyde's starting to not really be able to dissolve much at all, okay? But the ketones are similar in the fact the smaller they are, the more likely they are to be soluble in water. But again, it has everything to do with the carbonyl here having a dipole moment and it being able to hydrogen bond with the solvent, in this case, water. All right, any questions on properties and or naming of aldehydes or ketones? Okay, while you're typing into the Zoom chat there, I'm going to go ahead and stop sharing my screen and get back to video here. Okay, we're right at 12:40. So what I want to do is I want to go ahead and stop recording and start letting it do that and have anybody ask questions that you might have. Stop